Hi. Hi. Yeah. Good morning in my side. I'm in America, so um, I'm Haonan Zhao from University of Michigan Ann Arbor. My advisor is Professor Stephen Forrest, and we're pretty much focused on organic electronics. And today I want to talk about the stable and efficient phosphorescent blue OLEDs that we have been focused pretty much. The OLED team is focusing on the phosphorescent OLEDs for quite a while now. So I'm gonna introduce the phosphorescent OLEDs and the problems blue phosphorescent OLEDs are facing, and gonna introduce the two works that I've been working on. One is eliminating non-radiative decay in deep blue PHOLEDs using the host matrix amorphous phase control. And second is the PEP OLED, the newly proposed stable blue phosphorescent OLEDs using polariton-enhanced Purcell effects. So phosphorescent OLEDs can use 100% singlets and triplets due to their strong spin orbit coupling of the heavy metals. So the phosphorescent OLED can feature 100% internal quantum efficiency, makes them very promising for the next generation display and lighting application. The full-LED exciton usually has a typical lifetime of tau of microseconds, which is way more faster than the triplets without any spin orbit coupling, which are milliseconds. But it's still quite slower than the singlet emission, which is usually in nanoseconds. And on the right here, I just show this. There's like a typical OLED architecture, and give us how these energy of the triplets are distributed. You have error modes and substrate mode, and wave-guided modes and SPP, but these are all just radiative. So when we talk about blue PHOLED challenges, we usually talk about their efficiency, their lifetime, especially the lifetime. But the phosphorescent phosphor triplet energy are have radiative channels and also non-radiative channels, right? But the blue phosphorescent OLEDs have severe non-radiative and deleterious annihilation called triplet annihilation and triplet polaron annihilation. This is this is this is very dangerous because the blue exciton has around an energy around 3 eV. This can stack up to 6 eV via the triplet annihilation and triplet polaron annihilation. And 6 eV is well enough to kill the molecules and break them into fragments. And this caused the intrinsic degradation of blue PHOLEDs, also a source of um, uh, inefficiencies in blue PHOLEDs. So here is a chart of the red, green, blue, and deep blue PHOLED lifetime and their efficiencies. You can see that the lifetime uh, drops dramatically with the color goes to deep blue, and because this triplet annihilation and triple polar annihilation is energetically driven. So our strategy here is to engineer the exciton decay rates. We want to minimize the non-radiative decay rates and increase the radiative decay rates. So the first strategy is to control the non-radiative decay using host matrix amorphous phase control. So we have found that the typical stable, also commonly used host called MCBP, it aggregates and creates this so-called green boundaries and small crystals, and this can provide a path for the triplet and polaron to diffuse. Once these paths are established, the triplets and polarons from excited from the one dopant or the host, you can diffuse into the other dopant and quench the other triplets. This makes these deep blue emissive layers to be very inefficient. So we have found that mixing hosts with bulky host materials like this host here, SITRZCZ2, it's a silane group has it's a silane based host with a bulky silane group, and has it can suppress non-radiative quenching by